PLA, Programmable Logic Array. We'll talk about how to implement functions using Programmable Logic Array. These are the few PLD notations which I want to tell you. This is a fusible link for an AND gate, and in this it is represented by this. This is a fusible, all inputs are fusible and they are connected. Similarly, this is fusible OR gate and all the inputs are connected. So its output is basically A plus B plus C. This is A, B and C. So all fusible AND gate is represented by this gate. You don't have to put a cross at all the inputs. This is all fusible AND gate, all fusible OR gate where all the inputs are fusible. Now here there is or you can say this is a unprogrammed AND gate and unprogrammed OR gate. This is the third one. It is a programmable AND gate in which the fusible link at this has been blown off, and this can be blown off by giving high voltage. So this fuse is blown off, so output is AC. Similarly, you have an OR gate. It is a programmable OR gate where this fuse has been blown off. So according to this, the output is A plus B. These are non-fusible links, representation of AND and OR gate, and in this you have three inputs ABC in both, and they are non-fusible. So we just implement this by this. If they are connected, then it is. This is how you have. So you can have fusible links and you can have non-fusible links, and you have to represent them by this method. Next is a PLA, Programmable Logic Array. Programmable Logic Array in which both AND gates and OR gates, they are programmable. AND gates are followed by OR gates, but they are both programmable. So there is no decoder. When you have your inputs, there is no decoder. You can program your AND gates in such a way that you get the required number of minterms or the minimum possible minterms. Then you can use your OR gates depending upon the number of inputs. Let's have a function F1 and F2 which has to be implemented using a PLA. Now there is no decoder here. Earlier in a ROM we were generating all the minterms, but in this there is no need of generating the minterms. You should have minimum number of product terms. So what you do is you make a K-map. If ABC is the variables, sorry, 1, 0, 1, 2 and 4. So these are the inputs. So you have to write F1 in true form as well as F1 in complement form. Fine. What is F1? This is 1, this is 2 and this is 3. There are three minterms. So we have B bar, C bar, we have A bar, B bar, and we have A bar, C bar. This is 1. And if you take the max terms, then you can have BC, A, B and AC. This is how you can represent your F1 in true form as well as complement form. So this is the true form, this is the complement form of F1. Similarly, represent your F2 in true form as well as complement form. 5, 6, 7. F2. So what is F2? It's A bar, B bar, C bar. Then you have A, B and AC. This is F2. And F2 in complement form will be F2 in complement form will be, this is 1, this is second, and this is, so I have A, B bar, C bar, then I have A bar, C, A bar, B. This is what is the forms of F1 and F2 in both their true and complement form. Second is you have to make the function. If you have F1 and F2 in your circuit, then number of product terms will be 1, 2, 3. I can write the number of product terms. Will be 6. Number of product terms will be 6. If I have F1 in true form and F2 in complement form, F1 in true form and this in complement form, then also it will have 6 product terms. And the task is reduce the number of product terms. That is why we have taken both the functions in both the forms, true and complement form. If F1 is in complement form and F2 is in true form, F1 is in complement form and F2 in true form, then they will have AB and AC, they are common, so 4 product terms. The main aim is reduce the number of terms, and if both are in complement form, then also 6 product terms. So you have to do this job of comparing them. So when you have 4 product terms, that means you will implement F1 in complement form and F2 in true form. So what do is now you have the product terms. Generate only important product terms. Don't generate all the product terms. So first thing is make a PLA table and then draw its circuit. So first is the PLA table. Then write the product terms. Product terms. These are the inputs. Inputs क्या है? A, B and C. And then you have the outputs. F1, F2. So what is the product term? First is BC. So BC, this is not there. Is it present in both F1 and F2? No, BC is present in F1. Then you have AB and AC. AB is A, B. What is AC? A, C. AB and AC, they are present in both the functions, F1 as well as F2. So I'll have, and then the last term is A bar, B bar, C bar. This is A bar, B bar, C bar, and it is present in F2. So you will have F1 in its complement form and F2 in its true form. So F1 is in complement form, F2 is in. So I can just, why to make so much space, so much of space, F1, F2. So F2 is in true form and F1 is in complement. Then I have to draw the circuit. This is a PLA table. What is the circuit of a? You will have VC, you will have AB, and then you will have AC, then you will have अब ये कैसे आ रही है? इसको सब आ रहा है. This is not working properly. Let me have a better. A bar, B bar. C bar. So we'll have all the inputs. We have B and C. B, C. Rest of the fuses are blown off. A and B, A, B. Rest of the fuses are blown off. A and C. A bar, B bar. A bar, B bar, C bar. So A bar, B bar. So rest of the fuses are blown out. So we get these four product terms, minimum number of product terms. Now you have two outputs. F1 F2. F1 is in complement form. So here I will get F1 bar. Fine. Now what is F1 bar? BC plus AB plus AC. Fine. And what is this? A bar, B bar, C bar, AB and AC. This is F1 and F2. Now we want F1 and F2. I don't want the implementation of F1 bar. So I think I told you in one of the classes that if any variable is being XORed with 0, you will get F1. And if any variable is XORed with 1, you will get its complement. So if you XOR this with this is 0 and this is 1. So I want a complement. I want a complement of F1. So let me give this F1 bar. I'll get F1 here, and similarly I'll XOR F2 with 0 to get F3. So this is the final circuit for a PLA. In this, what you are doing is, it's programmable logic array in which both AND gates and OR gates are programmable. So when AND gates are programmable, that means there is no need to make use of a decoder to generate all the minterms. You can generate the product terms as many as you want. It won't be 8 as per the number of input variables, because input variables decides the number of product terms. So what we do is, we make k-maps, then we find out the true function of those functions in true form and complement form by using minterms and max terms. But all that function is in the form of sum of products. That is why I have written it like this. So this is also in SOP form, this is also in SOP form. So I'll get all, then I'll make the combinations possibilities to find the minimum number of product terms. That means AND gates becomes programmable. So here the number of product terms become programmable. What is the next task is to make the PLA table. So next PLA table is BC, AB, AC, this is this. Then in one column you will have the inputs, in second column you will have the outputs, and it will tell that which function is in true form, which is in complement form. It may happen that both are in complement. It may happen that one is in complement form, other is in true form, and it may happen that both are in true form. So there is no hard and fast rule. So according to that, I have just made the circuit. There are 4 product terms, so there are 4 AND gates. These are the fusible links. I showed you in the just when we started the lecture that what are the fusible links and how they appear. What are the PLD notations? So these are the fusible links. Whatever these links where there is no cross, they are blown off. Since they are both programmable, that means you have fusible links at the input of AND gates as well as the input of OR gates. So these are the fusible links. Then see which product terms are being used in which of functions. There are 2 functions, there will be 2 OR gates. These 3 product terms are being used in F1, but will get F1 complement. And these 3 product terms are being used in F2, and F2 is in true form. And finally, to get F1 and F2 in true form, you can actually make use of a XOR gate to get both the functions in their true form. If you XOR them, the function with the 0, you will get the function in its true form. If you XOR it with 1, you will get its complement. That is what we are doing.